Okay, the second talk for today is by Jonathan Weinberger from the University of Birmingham, and he'll tell us about synthetic fibered infinity one category theory. Go ahead.
Thanks a lot, Dan, for the introduction, and thanks all the organizers for this very nice event and letting me speak here. So I'm going to talk about joint work with Ulrich Buchholz that you can also read up on in this preprint here, and some work based on this from my PhD thesis, which I just defended in December at TU Darmstadt, supervised by Thomas Streicher. Okay, so in the introduction, I'll briefly talk about the objects that we're interested in, which requires a special variant of homotopy type theory to work in, which I'll give a brief overview afterwards. And yeah, then I'm also going to briefly just show how to talk about these objects and this kind of theory. And yeah, sort of the main part with the contributions are these various notions of families or functorial families or fibrations that this setting allows for. So we're interested in infinity one categories. The idea behind those is that these objects should be something like a category weakly enriched in spaces, meaning that instead of a set or a class of objects, we're going to have a space of objects, spaces of arrows, and composition is then going to be a continuous map between those arrow spaces. So this in particular means that composition of one morphisms is now determined uniquely only up to contractibility, which can be phrased as follows. Consider a pair of composable morphisms, then the space of possible composites, meaning a potential composite edge here and a two-cell witnessing the actual composition here, that space is going to be homotopically or topologically trivial, meaning it's contractible. So infinity one categories were introduced by Bodman and Vogt via the technical notion of quasi-categories in 73. And the theory was then considerably extended later on by Joyal and Lurie. And today they're relevant in different branches of modern day algebraic geometry, homotopy theory, and also other areas. So what's the way to talk about synthetic infinity one categories in HOT? So usually types are understood as homotopy types or infinity groupoids, but infinity one categories are more general than that because of the presence of potentially non-invertible arrows. So we do have path types in HOT, but what about directed arrow or directed hom types? So one approach due to Riehl-Shulman and also due to Joyal upon an independent suggestion was to extend HOT in such a way that we are now reasoning about simplicial homotopy types or simplicial spaces. And this then should make it possible to internally carve out those types that are in fact infinity one categories or even infinity groupoids. And in fact, by Schulman's strictification result from 2019, we can replace the higher topos of spaces by an arbitrary higher topos, so that such a theory would become a synthetic theory about internal infinity one categories with respect to an arbitrary infinity one topos. So in fact, this is going to be our setting. We're working out fibered infinity one category in Riehl-Shulman's simplicial homotopy type theory, oriented along real Verity's infinity cosmos theory, where the latter is a very general approach to model-independent higher category theory that yeah, I can't go into details about today, but it's been very important for this whole development in this type theory. So there's a lot of related and ground-laying work by several people on various directed type theories and directed univalence, some of which I've listed here. There's also work on fibrations of infinity one categories that has been very important, and Segal spaces or Segal objects, aka internal infinity one categories. I also recommend checking out a recent prototype proof assistant developed by Nikolai Kudasov, which you can even try out interactively online in this repository here, which supports the proof of some of these results from the Riehl-Shulman paper that the whole setup is based on. There also have been previous hardest talks by Emily Riehl, Denis Charles-Zizinski, Matt Weaver, and Ulrich Buchholz about topics connected to the theme from today. Especially Ulrich also presented parts of our work in this talk here last year. So how does Simplicial HOT constitute itself? So first of all, the idea is that in order to talk about directed arrow types, we should have something like an interval and maybe shapes derived from that, which type families can depend on in addition to the usual context gamma. So we do have this additional data here, psi and phi, which sort of capture these additional shapes. This bears some similarity with cubical type theory, of course. So Riehl-Shulman provide a whole syntax and a multi-layered type theory for that. We don't need to be precise about the syntax today. Let's rather look at the pictures that we get. So we start with the simplicial directed interval here. We can take finite powers of those, giving us the square and higher cubes and so on. We can carve out the two simplex and the higher simplices as well, and the two one horn, as well as other horns and other shapes, boundaries, etc. Furthermore, as a gadget, in this theory, we have what's called extension types. So these you can think of as pi types with side conditions. They were suggested by Lumsden and Shulman, and you can also find an instance as the path types in cubical type theory. So they work as follows. Consider given a shape inclusion referring to these shapes that I showed you on the previous slide, and a family depending on the larger shape, and a partial section depending on the smaller shape. We're interested in sections that strictly extend this given partial section. And how do we get those? Well, by introducing a new type former, this extension type, which is this pi type with the angular brackets here, whose terms are exactly the extension, the strict extensions of the partial section. So semantically, these arrive as pullbacks, but the point is that we really have those internalized in our type theory with the strict computational behavior. Okay, how can we define synthetic infinity one categories in there? So first of all, we can define the Hom types as certain extension types with respect to these arrow types by considering maps from the interval into our type that restrict appropriately on the boundary. We can also consider relativized version of this in a family, which geometrically looks as follows. So considering a fixed arrow in a base type, we can consider the type of all those arrows H that lie over this arrow W. And we can do so also for the two simplices or all the other shapes. So now Riehl-Shulman make the following definitions. A type with a weak composition, or a Segal type, is a type that is local with respect to the two one-horn inclusion into the two simplex, which exactly endows each type with such a weak composition operation as we would like to have for infinity one categories. So this has been observed to be able to being formulated as this just single finitary condition in the semantic setting by Joyal for bisimplicial sets. So it's very nice. We don't need to worry about higher coherences and stuff. It's really just this single equivalence condition here. And now to obtain actual infinity categories or RESC types or complete Segal types, we need to add the RESC completeness condition, which is like a local univalence condition imposed on the given types, saying that the identity types coincide with the isomorphism types, where the latter are derived from these directed Hom types that we've looked at before. And synthetic infinity groupoids or discrete types are now types where all the arrows are invertible. So from now on, when I say infinity category or synthetic infinity category, I mean infinity one categories, because these are the only ones we're considering here today. Okay, so what's the deal with those fibrations or co-Cartesian families? So in homotopy type theory, any type family transforms covariantly with paths, meaning that given a path in the base, we get an induced transport functor between the fibers. And we can ask, could there be a directed principle where families transform covariantly with directed arrows? And it's possible to consider this in this Simplicial hot. So Riehl-Shulman have done this in the groupoidal case, where the fibers are synthetic infinity groupoids. So these are called covariant families or synthetic left fibrations, if you're more familiar with this terminology. They've also considered briefly the two-sided case with mixed variants, co and contravariant. So together with Ulrich, we've generalized this to the categorical case where the fibers are now resc. And this gives the notion of co-Cartesian family. Furthermore, in my thesis, I've considered other notions of fibration based on that. And these are all sort of, from analytic higher category theory, known important notions of fibrations. In particular, they also tend to support a principle of directed arrow induction, which we can understand as a type-theoretic Yoneda lemma. So what's a co-Cartesian family? First of all, we need to say what a co-Cartesian arrow is. So given a family like this, and fixing an arrow u in the base, an arrow f flying over is said to be co-Cartesian if it satisfies the following universal property for any v that we can post-compose with here, and any h that we can post that lies over the composite. There exists uniquely up to homotopy an arrow g, making this whole, filling this horn and yielding a composite triangle. Okay, that's what a co-Cartesian arrow is. This picture may look familiar from the one categorical setting to you, but the point is that now we can formulate all this in this type-theoretic syntax involving a lot of these extension types here. Okay, and a co-Cartesian family now is one where, first of all the types involved should be resc. So like the base type and the fibers should all be synthetic higher categories. And now such a family is co-Cartesian if we have enough co-Cartesian lifts, meaning any given u together with an e lying over the initial point like this. There exists a strict co-Cartesian lift of u, and it turns out that if it exists, it will also be determined uniquely up to homotopy. And this in fact induces a transport operation. So it gives a notion of functorial family, which on arrows acts as is indicated here briefly via the universal property of the co-Cartesian arrows. So semantically, these correspond to covariant infinity presheaves valued in the infinity category of small infinity categories. So we get several examples, such as the codomain projections, the domain projection in the case that the base is all pushouts. And also we can construct the free co-Cartesian fibration and prove that it satisfies the desired universal property. Also, we obtain a characterization in terms of the existence of a certain left adjoint right inverse, meant in the synthetic homotopy coherent sense. The idea is that this left adjoint right inverse, which is supposed to exist as the left adjoint to a projection map, the idea is that this left adjoint exactly models the co-Cartesian lifts here. And what is nice about this criterion is that a lot of the desired closure properties for this notion of fibration comes out of just the sort of formal shape of this criteria. We can also prove the Unita lemma for co-Cartesian families, or at least some versions of it. So this says that sort of given a family that depends on arrows with a free target point, that the generalized elements of those are determined just by evaluating at the identity. And yeah, I'm afraid I don't have time to discuss this today further, but you can watch Ulrich's hardest talk from last year, where this is discussed in detail. Okay, now we can vary this notion just by dualizing it to obtain a notion of Cartesian family, which is going to transform contravariantly. And we can take the conjunction of these conditions giving rise to the notion of bicartesian family, which transforms in both directions. And turns out that the transport functors form an adjoint pair in this setting, also known from the classical theory. So examples are given by the family fibration. So this is essentially what you get by taking this free co-Cartesian fibration construction on a fibration, or the what's called Artin-gluing fibration, both which suppose that the base has pullbacks. And applications of those exist in one category theory, for example, in what's called the fibered view of geometric morphisms, due to Benabou, Moons, and Gibladze, and later further developed and applied by Streicher, Lietz, and Frey. So the central result there is that the geometric morphisms over a fixed topos can be characterized as fibrations of toposes, where the fiber at the terminal element is given by the domain of the geometric morphism, and the one direction is given by this Artin-gluing construction. So going from from a geometric morphism, we can get a fibered topos by the gluing. Now one can further ask which fibrations of one categories are of the form that they are the Artin-gluing of a Lex functor. And the answer is provided by Moons' theorem from his PhD thesis at the University of Louvain-la-Neuve from the early 1980s. Namely, this is exactly given by those fibrations which are Lex bifibrations satisfying a further condition. Namely, they are supposed to have stable and disjoint internal sums. Okay, what does this mean? So first of all, recall that a bicomplete category is Lex-tensive if, in a canonical way, the product of the slices coincides with the slice over the coproduct of a family of objects. And there is also a fibrational version of that, which we can just formulate in this synthetic setting. So first of all, a Lex fibration should be a bifibration satisfying a version of the Beck-Chevalley condition, which is illustrated here. So those have been considered for quasi-categories in some work by Hopkins and Lurie. The condition is that given a dependent square over a pullback, where we have a configuration with Cartesian arrows here and a co-Cartesian arrow here, then the whole square is a pullback if and only if this arrow here is also co-Cartesian. And furthermore, these internal sums should be stable, meaning that co-Cartesian arrows should be stable under a pullback along arbitrary morphisms. And they should also be disjoint in the sense that the fiber-wise diagonals of co-Cartesian arrows are also co-Cartesian. Okay, this gives the notion of a Lex-tensive or Moons fibration. And yeah, it turns out that one can adapt the proof that, for instance, Streicher gave in his lecture notes on fiber categories a la Jean Benabou to this synthetic higher setting, which gives an equivalence between the type of Moons families and the type of Lex functors into small Lex categories from the base Lex category here. So just to give you an idea of how this equivalence works. So from functors to fibrations, we can go via the gluing here. And what about going the other way? Well, okay, so from a family, we have to construct a functor into a Lex category. So the Lex category will be given by evaluating the family at the terminal object. And how is the functor going to be defined? Well, we just have to define it on the points, on the terms of the type, which is a specialty of the setting here. So it's really uniform, and type between two maps, which happen to be Segal, is automatically going to be a functor. Sorry, any functor between two types which happen to be Segal. Sorry, any map between two types which happen to be Segal is automatically a functor. Okay. So what do we do? Well, first we start with some point, and sort of we want to end up in the fiber over here. So what we're going to do is first we take the terminal element of the fiber over the point, and then we just take the co-cartesian transport along the terminal projection here. And it turns out that those two, so this gives us a map in the other direction. It turns out that those form a quasi-inverse pair. So my thesis, I've also considered other notion of fibration, a sort of fibered notion of fibration, where so the fibration is supposed to be a fiber-wise map between two families, such that given a vertical arrow over here, so given an arrow f which lies over an identity or a point, this is supposed to have a co-Cartesian lift in F along phi, which is co-Cartesian in the sense of this map here. And those are important to, or those are at least technically very helpful to study a notion of two-sided Cartesian family in this setting. So those are mixed variance families into variables. They can be presented by spans, where on the left we have co-Cartesian fibration, and on the right we have a Cartesian fibration, where these lifts have to satisfy certain compatibility conditions. So externally, those model functors of this signature here, and those can be understood as something like infinity one categorical distributors or profunctors, where here we have the category of small infinity categories rather than just spaces. And understanding those two-sided Cartesian families as a kind of fibered fibration in this way, again, gives us a lot of these infinity cosmological closure properties. That's why it's technically nice to take this viewpoint. And they also, these two-sided Cartesian families also validate a Yoneda lemma, which again we can understand as directed arrow induction. Now with respect to two base types, and both, one where one is being acted upon covariantly and the other one contravariantly, respectively. Okay, so some perspectives include work on now RESC universes. So in this work, we're sort of employing or relying a lot on some form of Groten deconstruction, switching between the fibered and the indexed view, where the indexed view uses the universe, namely the type of all small types. But in fact, we are interested in a type of, let's say, the type of small RESC types, or the type of small discrete types. And in fact, we can single it out from the universe as a subtype, but it won't be RESC. So we need some other techniques to yield an appropriate construction for this purpose. And this seems somewhat connected to a synthetic notion of flat or synthetic infinity one Condorcet fibration. And sort of the whole setting also demands that the type theory is going to be extended by modalities of what's called cohesion. Then we're also interested in augmenting this type theory further by type formers for opposite types and twisted arrow types. This seems doable in a multimodal framework due to Licata, Riehl-Shulman, or the later version by Gratzer, Cavos, Neutz, and Birkedal. And a very nice application of all of this would be a synthetic development of some parts of higher algebra. So let me conclude with the references. I've also already mentioned the preprint here. We've on the semantic side relied a lot on results by Nima Rasech on Cartesian fibrations of complete Segal spaces. The work, of course, crucially builds on Riehl-Shulman's paper where Simplicial hot was introduced and the beginnings of these theories were developed. Also on Verity's book on infinity cosmos theory, which is to appear soon. Mike Schulman's 2019 result on strictification of univalent universes has considerable implications for the semantics of our theory. There are the lecture notes by Thomas Streicher, out of which I've generalized some parts in this setting. And then there's my dissertation from last year to be published hopefully soon, sometime this year, to be freely available. So thank you all very much.
Great, thanks very much, Jonathan. That's all. Thank Jonathan. Okay, so people can